I've knocked this thing. It seems to be at a funny angle. Give me a second to try and straighten things off. Looks weird. Okay, our goal today is to do section 13.2, and we're essentially going to be finding how do you get the derivative of a vector function at a space curve. So let's jump right in. Here is a generic vector function. We'll call it f of t, g of t, h of t. So an example might be t cubed plus t, 3 sine of 2t, and e to the t minus t, right? Well, so how do you find the derivative of vector function? Well, it's actually intuitively pretty obvious, I think. You find the derivative of each of the components. There you go. I'll even put a little box around it. Does that seem reasonable, that if you wanted to differentiate it, does it seem reasonable that all you would do is differentiate each of the pieces? So for instance, if I gave you this function here, and I said to you, differentiate it, find its derivative, r dashed of t, you would differentiate this guy, which is the power rule. You then differentiate this guy, and if you differentiate 3 sine of 2t, you will get 3 times the cosine of 2t. But is that all you get? What else is missing here? If you differentiate 3 sine 2t, you don't just get 3 times cosine 2t. It's actually a little baby chain rule. You get times the inside function. So you get times another 2, which means that you actually get 6 cosines. So you get 3t squared plus 1 for the first component. You get 6 cosines for the third. If you differentiate e to the t, you get e to the t. Differentiate that, you get 1. And there is our answer. So if you want to differentiate any space curve, all you need to do is differentiate its bits. So if you know how to do differentiation from Calc 1, you're going to be able to differentiate a space curve.
I have a quick question, Professor.
Sure.
Looking at the R vector, is
Yes.
why is there a 1 up there to the corner?
Oh, that is the dash symbol, the derivative symbol.
Oh, okay. Oh, that's derivative symbol. Okay, I see what you did.
You can also see the derivative written down using that notation. So these are equivalent. We good? Right. Now, way back in the day when you did Calc 1, you would be dealing with a two-dimensional situation, right? So you'd have your function y equals f of x. And if you went and found the derivative, say at, I know, this point here, wasn't the derivative, one of the meanings of the derivative is the slope of the tangent line at that point. You remember doing that? Essentially, that's where derivatives came from the tangent line problem. So if you find f dashed of x, it's the same as finding the slope. Now, what does that look like in a 3D world? Well, it's a little bit more complicated what you're actually getting. So imagine we have our x, we have our y, and we have our z. And let's imagine that this is the space curve, r of t. If you choose any point and you use the derivative function, so let's suppose I take that point there, what I am getting is not the slope of this line. which is also called the tangent line. I'm not finding the slope, because if you plug a number in here, would you agree you get a vector, some number, comma some number, comma some number. What you get, in fact, is the slope. Well, I shouldn't say slope. You get the direction, that's a better word. Vector. So basically, you get a vector that tells you what the direction, how about that, at the curve is. So an analogy that I give is, can you imagine that R of t is a roller coaster, right? And since I've got this guy here, I'm going to have to do my roller coaster again. And at this point here, right, at t, the roller coaster is broken, right? The track's busted, you're going to die. Right? As you go around that roller coaster, when you get there, won't you shoot off to your death at a certain direction? Agreed? Shoot off to your death. That is what the derivative vector is telling you. It's telling you the direction at that point on the curve. Now, can you imagine if it was broke at different places? Like if it was broken here, wouldn't you be shooting up into the air before you die? Right? If it was broken here, wouldn't you be shot like a bullet towards the ground? So at every different point on that curve, won't the derivative vector be different? As you'd expect it to be. If you did a two-dimensional, wouldn't you get slopes at different places? Right? Would be different. Does that help you get a kind of visual idea of what finding a derivative does? Now, the application of it, in other words, getting the value for a derivative, is probably the easiest piece of the process, because all you need to do is differentiate who this guy is, differentiate who this guy is, and differentiate this guy. So I'm going to pick another function and find its derivative and then show you something else. So suppose I've got a vector function, a space curve, and I'm picking nice, easy, quick to do guys. Suppose I have that guy. If I want to find its first derivative, differentiate this guy, 3t squared plus 1. If I want to find this guy, you get 2. And if I differentiate this guy, you get e to the t. Are you all comfortable with the derivative? Derivative, derivative, derivative. So far, so good. What would you do to find the second derivative? So it's not an 11, it's 2 little dashes. Second derivative, what would be the most obvious thing to do to get that? I'll take any takers. Second derivative, what should you do?
That'd be 6t 0 and e to the t. So
Essentially, don't you just differentiate the first derivative one more time?
yeah.
And when you did Calc 1, you found f dashed of x, right? Well, wasn't the second derivative f double dashed of x? Wasn't that just the derivative of the first derivative? And if I wanted the third, actually nobody wants the third, but if I wanted the third, wouldn't I just differentiate it again and so on until I got whatever I was looking for? So the rules for finding first and then second derivatives are very similar to what you would do in Calc 1, which means that you have to be a little bit up to speed on differentiation, right? And what am I getting at? Well, sometimes you're going to have to do a product rule. Sometimes you're going to have to do a quotient rule. Sometimes you're going to have to do a chain rule. Remember those basic rules that you need when the function's a little bit more complex than just t cubed, right? T cube's just called the power rule, by the way, right? So let's pick one that's got some stuff going on that requires a little bit more work. Okay, suppose we start with the space curve R of t. And this time it's going to be 4e to the 3t, t times sine t, and 1 plus t over 1 take away t. And we're being asked to find the first derivative. I'm going to take each one separately, what we should do. So let's ignore those two. If you want to differentiate this one, this is in fact a chain rule. And a chain rule is like a function of a function. So if I wanted to differentiate this, you would get 4e to the 3t times the derivative of the inside function, which in this case is 3t. And the derivative of 3t is 3. And so you end up, when you're finished, with 12e to 3t. So that would be an example of me using the chain rule, right? Now, if I want to do this middle one, t sine t, then I have to think about how I'm going to get its derivative. And that's going to be a product rule. So I'm going to call it y equals. And when you do a product rule, one of the functions, in this case, that guy is f, and the other function is going to be called g. And its derivative is f dash g plus f of g dashed. That is the product rule formula. That's the formula you should use when you're trying to differentiate two things multiplied. You know, like t cubed sine t, right? And e to the t times cosine t, right? Square root of t times t plus 1, right? Whatever it might be, two things multiplied, this is your formula, the product rule. So let's see what we get. If you differentiate that, you get 1, you leave g alone. So it's 1 times sine t. Plus, you leave that alone, and you differentiate sine t, and you get cosine t. So essentially, the derivative is sine t plus t cosine t. So sine t plus t cosine t. Now, the last one in our set is this fraction. And if you have to differentiate a fraction, you're going to have to use a different rule, and it's called the quotient rule. Quotient's just an old name for fraction. So it's a quotient rule. And God, how would it? Is it 6 months since the last time you did differentiation? Or Calc 1 at least?
Last time I took Calc 1 was winter of 2019.
Okay, then you are definitely going to think a little bit harder. Does anybody remember the formula using f and g? And when you do a quotient rule, you always call the top guy f and you always call the bottom expression g. Can anybody remember the formula for the quotient rule using f and g? I'll start at f dash g. Take away f of g dash. Do you know it looks just like the top, doesn't it? With a subtraction. The big difference is you then divide by whatever g is squared. So let's see what we get here. F dashed is the top. If you differentiate 1 plus t, you get 1. Leave g alone. Subtract. Leave f alone and differentiate the bottom, and you get -1. All over 1 take away t squared. So you get a 1 minus a t, take away Well, if you multiply a -1 by that, it makes everybody positive. So you end up with +1 plus t. With the whole thing on the bottom squared. And these cancel, and these combine. And the final answer ends up being that guy. So if you want to differentiate this fraction, the answer is 2 over 1 minus t squared. So 2 over 1 minus t squared. And that's us finished the derivative. So to be able to do these, you really need to be up, up on the techniques of differentiation. And that the three techniques are product rule, quotient rule, and chain rule, right? They're the most likely ones you're going to have to deal with in these questions. Any questions? We know the how to do it, right? The particular way to tackle it, right? Procedure. But do we have enough practice at these? I don't think so. So I think we should spend a little bit more time just differentiation things, finding derivatives, just to, get the cobwebs out. So. So here we have the square root of t squared plus 3, comma, the natural log of t squared plus 3, and e to the 5t squared. Now I've picked this particular example. Actually, I can put it in. I can do this particular example. Now I chose it because it uses the chain rule in every case. So every single one of these is a chain rule. Now there is a little difference for the first one. If you're going to differentiate a square root or a cube root, you need to turn it into a fractional power. So square roots have to be called a half. And I don't need to alter the other two, so I'm just rewriting them again. When you differentiate something and you use the chain rule, one of the things you need to identify is what's called the inside function, because that's going to help you get the answer. In this one here, the inside function is t squared plus 3. In this one here, it's 5t squared. And in this one here, it's t squared plus 3. So let's start with the derivative now. If you want to differentiate this guy, imagine the main function is a half, right? It's something to half. So the rules are multiply by the power and reduce the power by 1. Right, so it's a power rule. Multiply by the power and reduce the power by 1. And because it's a chain rule, because that guy in there isn't t, in this case it's t squared plus 3, because of that, you finish with the derivative of the inside function. So you have an extra 2t. Now, that guy and that guy cancel, and you're left with a t and a t squared plus 3 to -1/2. Are you happy with the first one? Multiply by the power, reduce the power by 1, that's this bit, and then finish with times the derivative of the inside function. Well, if you differentiate this, you get 2t. Right. Middle one. If you want to differentiate a log, what is the derivative of, say, log x? Log x, what's its derivative? Any takers? Okay, here it goes. It's 1 over x. So if you differentiate the natural log of t squared plus 3, it's 1 over t squared plus 3, right? If it was if it was log t, it'd just be 1 over t. So log t squared plus 3, so it's 1 over t squared plus 3. And then you finish with the derivative of the inside function, which in this case is times 2t. And when we tidy that up, it looks a bit like this guy. And the last one is e to the 5t squared. If you differentiate e to the 5t squared, like e to the x, you get e to the x. E to the 5t squared, you get e to the power of 5t squared, times the derivative of the inside function, which is 10t. And typically you'd put that first and then the ugly power there. And we have differentiated that one, and that's as good as it's ever going to look. We've differentiated the middle one, and that's as good as it's ever going to look. But this guy here can be made to look prettier. I call this style points. And the rules for style points are: 1, make it look like the original. Now, the original had a square root. This doesn't. So that's the rule I'm going to use. The second rule is factor the heck out of it. That's normally not going to be an issue with these questions, but occasionally you may be able to pull out a common factor of t. And then the third rule is if it's trig, right? So if it's got sines and cosines and things like that in it, see if there's a trig identity that you can simplify it with. So that's the rules of simplification. I call them the style points, right? You get more points for looking stylish. Now this fella is going to be rewritten as t squared plus 3 to the positive half. And then that allows me to turn it back into a square root. And the other two, they were fine. I didn't need any style points on those guys. They're already as nice as they're going to get. There is our derivative. How are we doing? Is it slowly coming back, all the various things that you need to do?
Slowly but surely.
Slowly but surely. Okay. So let's take a side issue for a minute. Since we're going to be dealing with t's, I'm going to write this formula in terms of the variable t. So on this little page, I'm going to be writing a function and then next to it what its derivative is. And so as we go through today, if we come across one, I'm going to say, see, that's its derivative. Hopefully by doing this, it will help you to remember all the various functions you should know how to differentiate. So the first one is going to be a times t to the n. So this is called the power rule. And this is the rule that you're going to use when it's 5t cubed, 6t to the half, t to the negative 7, anything that has a power of t. And that power of t can be t cubed, it can be t to the half, it can be t to the negative half. It doesn't matter what it is, any power will do in general. And the rule for that is multiply by the power and then reduce the power by 1. Called the power rule. So that's t cubed, for instance, gets you 3t squared. That's that rule. Most people remember that rule by doing it in English. Multiply by the power and reduce the power by 1. That's kind of what you say yourself. But that's what it looks like algebraically. My favorite function in the world to differentiate, because it's the one I don't have any point or any problems remembering. What is the derivative of e to the t?
E to the t.
Yeah. Isn't that probably the easiest one to remember, right? There's nothing much going on there, right? Now, this one's a little bit trickier, and we've already used it once over in one of the earlier questions. The derivative of 1 over, the derivative of log t, I put the answer in, not the question. What is the derivative of the natural log of t?
1 over t.
1 over t. I kind of got that back to front. I told you the answer, but not the question. Right. Now, let's put in some of the trig ones. Sine cosine, tangent. If you differentiate a sine, you'll get a cosine. If you differentiate a cosine, you get a negative sine. If you differentiate a tangent, you'll get a secant squared. Are we good? Right, now there are three other trig. There's the secant, the cosecant, and the cotangent, right? I'm not going to put them in the list unless one appears, and if one appears, I'll tell you what it was. But for instance, if it was the cotangent t, it would be negative cosecant squared t would be the answer. It's a little trick for remembering when the thing is positive and when it's negative. And the trick is, if it starts with a c, its derivative is negative. So if it starts with a c, its derivative is negative. So since I've mentioned the cotangent, if you wanted to differentiate the cotangent of t, the answer is negative cosecant squared t. But these ones are less likely to appear, so that's why I don't want to overwhelm you with a lot of functions that you never actually get to differentiate, right? I mean, there's tons of other functions, but that's a good starting point, right? And when we come across new ones, I'll go back to this list, put it over there so I can find it, and we'll be good. So let's see if I can find any more derivatives. Okay, and this one is actually straight out homework. It's a version equation 15. The space curve is the tangent of 5t, comma, the secant of 8t, comma, and 1 over t to the 4. And I'm immediately going to go to my little list. If you want to differentiate secant t, the answer is secant t tangent t. So you might want to get a hold of a little list like this. Right, so we're ready to find its derivative. And I'll put these guys on here. Right, I want to differentiate the tan of 5t. If it was just tan of t, I could use this, and I wouldn't need to do anything extra. But technically, because that's a 5t, it does make it a little baby chain rule. Most of what we're going to do is exactly what you'd expect. The derivative of tangent is a secant squared. So the derivative of tangent 5t is secant squared 5t, right? That seems reasonable. But finishing with times the derivative of the inside function. And the derivative of 5t is 5, and that's why there's an extra 5 there. Now, the derivative of a secant is secant tan. So the derivative of secant 8t is secant 8t tan of 8t times. Well, because it's not just secant t, but the secant of 8t, it's a chain rule. And we always finish with times the derivative of the inside function. Well, derivative of 8t is 8, so that's why there's an 8 there. Now, if you want to differentiate 1 over t to the 4, you have to rewrite it as a power of t. And 1 over t to the 4 is t to the negative 4. Great. So now I can do the power rule. Multiply by the power and reduce the power by 1. Agreed? Now, style points. Nothing wrong with that, leave it alone. Nothing wrong with the middle one, leave it alone. This guy has to look like the original. And the original was a fraction, so this one's a fraction. Now we're finished. This one is Again, straight out the homework. This is a version of 16. We're being asked to find the derivative of this fella. And it's e t to the power of 9. That's weird. -1, which is actually remarkably simple, and the natural log of 1 plus 5t. So I have a really ugly power of e, I have a very easy number, and I've got a slightly difficult log. This fella here is a chain rule, right? If it was e to the t, be e to the t. So it's e to that guy. So the answer is, if you differentiate e to that guy, you get e to the inside function times the derivative of the inside function. And the derivative of t to the 9 is 9 times t to the 8. Are we comfortable about where that 9 times t to the 8 extra bit that came from that one is? Right? It's e to that guy, done, times the derivative of that guy, which is this piece here. Now, the number -1, like every number, if you differentiate, gets you 0. And this fella is a chain rule. It's a log of somebody. And if you want to differentiate the log of somebody, the answer is 1 over that somebody. So it's going to be 1 over 1 plus 5t. Times what number? It's not just 1 over 1 plus 5t. What's the derivative of the inside function going to give me?
Times 5.
Times 5. To save a line of working, can I kind of do that and sort of squeeze it in? And all of these guys are as good as they're going to get. So style points are done. We are finished. This is part of what you do in 18. So it's this fella. And we're going to find its derivative, amongst other things. But the derivative would definitely come first. The first function is that. If you want to differentiate this guy, there you are. None to see here. Pretty easy to do. Now the middle one. Would you agree that this is two things multiplied, so we have to use a product rule? So that's going to be the f, and that's going to be the g. So to get its derivative, it's going to be f dashed g plus f of g dashed. If you differentiate that guy, you get 1. You leave the second piece alone. You leave the first guy alone, and then you differentiate e to the 2t. What's missing? Because that isn't actually correct. I've missed something. When I found g dashed, right, the derivative of e to the 2t, the answer is e to the 2t. But what's also missing? Because that's not the full answer. E to the 2t.
Times 2.
Times 2. And can I stick the 2 at the front? That way I don't have to rewrite it all. And that means we now have the middle answer, which is e to the 2t plus 2 times t, e to the 2t. Now when you get to the last one, which is this one, you're really playing with fire here. This function is two guys multiplied. So it is definitely going to be a product rule. And when I get a difficult product rule, or a difficult quotient rule for that matter, I tend to do the working a little bit different. Over here, I write down who f is, and then underneath, I write down its derivative. Then I write down who g is, and underneath that, I do its derivative. Now, that bit work, not an issue. This bit is the issue. If you want to differentiate e to the power of t to the 4, you do get e to the power of t to the 4, and it is a chain rule, isn't it? The inside function is that ugly power. So that means you also get a times 4t cubed. So you would write it down as 4t cubed e to the power of t to the 4. So that's what g dash does. Now it's a matter of plug and chug, right? I just plug in the bits and I'm good to go. So the derivative is f dashed, which is 1, times g, which is that guy, plus untouched f, and g dash, which is this horrible mess. And while I'm at it, I'll do the style points here. This guy just becomes e to the power of t to the 4. These combine, so you now have 4t to the 4, e to the power of t to the 4. And that goes here, and you're finished. So if you're going to get the derivative of this space curve, you had to use product rule and a couple of chain rules on top of that as well. How's this looking? I'm hoping every one I do gets a little bit easier because you've seen, okay, I remember doing product rule now. I kind of remember the chain rule. I haven't done too many quotient rules, but they do exist. Do you
Just
need to see? Yeah.
it's just a lot to take in, especially that it reminds me a lot about of Calc 2, like how there's like a million different little moving parts.
Yeah, and this is just differentiation. And we are going to be doing later today, integration, which means you're going to have to, you know, hopefully that's a little bit closer, right? You've done that a little bit, you know, maybe last quarter if you're lucky, or two quarters ago perhaps.
Just last quarter. For Calc
Right,
2.
so that one's going to be a little bit fresher in your mind, so hopefully that makes it a little bit easier. And what we've done so far, okay, if I give you a function and say, look, I want r dashed of t, are you comfortable? You could look it up and get, you know, if you get lost, if you forgot that tan was secant squared, you could eventually get it, right? Product rule, quotient rule, chain rule as well. Can we move on? You want more?
I'm good.
Anybody got? We good?
Yeah, we can move on.
Let's move on. Right? I know there's going to be other, you know, you're going to do your homework and you're going to say, oh, wait a minute, I've forgotten the derivative of, you know, insert function here. If that does happen, don't you just go looking up your textbook or look up the internet and just do a search like table of derivatives? That'd probably be the simplest search, right? And you'll find somebody has written down every conceivable function that you would want and its derivative, and you know, you get it from there. Okay, so let's look at integration then. So imagine I have a space curve r of t. If I want to integrate it, it'll look like this. Isn't that almost identical to what it looked like in Calc 2? And you might have an a and a b in it, right? Most of the time you get an A and a B in it, right? So how do you do it? Well, let's suppose I want to find the integral of a space curve 0, 2, and my space curve is 8t to the 4 plus 1, 2t minus 2, and e to the t dt. Now, I'm sure for everybody here, or almost everybody here, you have never seen how to integrate a space curve, right? Well, we've just finished finding out how to differentiate a space curve, and wasn't it pretty much do what you would do, but do it 3 times, right? Differentiate the first piece, second piece, and third piece. So to integrate this guy, right? So imagine that the space curve was written down as a function of t, and then the nibble function, and then the last guy, like this. You integrate, I'm in a short room here, you just integrate each one separately. Oh, that's not too bad, right? So what would that look like? Well, you'd find the integral from 0 to 2 of 8t cubed plus 1 dt. Then you'd find the integral from 0 to 2 of 2t take away 2 dt. And then you'd find the integral from 0 to 2 of e to the t dt. In fact, if you start what we did on Monday, isn't it almost always the rule that if you want to do something to a space curve, you just do it to the thing 3 times? Wasn't that how we found the limits? Right? You found the limit of each one separately. Isn't that how you differentiate it? You differentiate each one separately. How do you integrate them? You integrate each one separately, which means that we have to know, or remember, whatever you want to call it, how to do integration. So here goes. This one here, first one. Power rule. Add 1 to the power and divide by the new power, which is 4, gets me that. If you want to integrate 1, you get 1t. And you evaluate it from t equals 0 to t equals 2. Well, if you plug in 2, you get 2 times 2 to the 4 plus 2. Take away a whole load of nothings. 2, 4, 8, 16, 30. 2, 4, 8, 16, 32. Add 2 gets you 34. 34 take away nothing is 34. So the first answer is 34. Have you noticed that we are going to end up with a vector when we're finished? So when you integrate a space curve, the answer you get is a vector. That's kind of weird, because when you did it in Calc 2, wasn't the area under a curve what you got when you integrated something, right? You got a number. But when you integrate a space curve, you're going to get a vector. We've just found the first component. Right, the second one is this guy. Right, if you use the power rule, you add 1 to the power, divide by the new power, you get that. The number 2, you integrate it, you get 2t. You evaluate it at t equals 0 and t equals 2. If you plug in 2, you get 2 squared, take away 2 lots of 2, subtract nothing squared, take away a whole load of nothings. 4 take away 4 gets you 0. That's the middle one. When you do the last one, you integrate e to the t, you get e to the t. Evaluate it at t equals 0 to t equals 2. That's going to get me e squared, take away e to the 0. And that's just e squared, take away 1. So there's your integral. It's a vector. Now, if a derivative can be thought of as, here's my little picture, as you shooting off to your death, right? So when you differentiate something, you're essentially getting the direction of the curve at that point. What on earth is the integral? Because that basically is a vector, right? Maybe it's that vector there, right? Well, it's a little bit harder to explain, but in a very, put two veries in front of that, rough idea. Can you imagine that you're starting at t equals 0, and the space curve does whatever it does, and this is t equals 2, right? Can you imagine the journey of the aircraft as it flies from its first 2 seconds, right? And it's zigging, zagging and doing its thing, right? At every single point on its journey, can you imagine that you're going in a certain direction? This fella here is essentially the average direction that the vector would go in. So although you're zigging and zagging here, the accumulative effect is you're going that way. So how could you use that? Imagine that you were looking at an aircraft that was flying towards your territory, and you were trying to figure out where's it really going. Now, aircraft probably, if they know that they're being seen and radar is picking them up, would you agree it's probably a good idea not to go in a straight line because they'll be able to shoot you down pretty quickly. So you zig and you zag. Secondly, don't use zig and zag so that they can't tell where you're heading. If I know what this thing is doing, can't I tell where it's heading by finding its integral? You're not disguising it because the net effect is you're going that way. At least based on the 2 seconds I saw it. Right. So there's an analogy for you. Let's do some integration. Right, if you're going to integrate things, the key things to remember are the following. The first one is the power rule. It basically says if you want to integrate a times t to the power of n, right? 5t cubed, 7t to the half. You add 1 to the power and you divide by the new power. So an example of that might be 3 times t to the 5. You add 1 to the power, you get 6. Divide that by the new power, divide it by 6, and you get a half. So the integral of this power is 1/2 t to the 6. You can always check that you've done it correctly. If you differentiate this, shouldn't you get back to 3t to the 5 if you've done it right? So that's the power rule. The second rule is substitution. For instance, if I wanted, and so this isn't really a formula, so I can just show you the process. If I wanted to, for instance, integrate that guy, the method that I would use to integrate it would be to use substitution. And what you do in substitution, can someone tell me for this function, what is the use of?
T cubed plus 1.
Great. Now you take this guy and you then differentiate it with respect to t. You do the crossover. Then you divide both sides by 3t squared to isolate the dt. This integral will now become 6t squared. The bottom becomes the square root of u, and the dt gets replaced by this guy, which is 1 over 3t squared du. Typically what will happen then is you get a lot of cancelling, the t squares kill each other off, those two numbers reduce, and we're now going to be looking at 2 over the square root of u du. So the idea of substitution is that you take an integral that's really difficult or impossible to do, and by choice of a substitution, a u sub, reduce it into a different integral which is easier and hopefully doable. Now, if I wanted to do this guy, I have to write it as a power of u. So I can use the power rule. So a square root is a half power, but it's on the bottom. If you bring it to top, anything on the bottom becomes negative. So you get that. You can then use the power rule, which says add 1 to the power, gets you a half. Divide by a half is the same as multiplying by 2. That's why you get a 4 there. You then turn it back into square roots, and to finish with, you turn it back into t's. And that guy is your answer. And technically there's a whole load of plus c's going on, but I'm skipping that just for convenience. Can you remember the substitution rule? Does it come back to you now? Or you go and watch some videos and get up to speed. So far so good? Right. Now there is a third rule that will sometimes happen. And this third rule is called integration by parts. If I wanted to, for instance, if I wanted to integrate t squared natural log of t, I can't use a power rule because it's not t squared on its own. There isn't going to be a guy in the table of integrals for somebody that looks like that. U sub will not help me. Integration by parts is essentially the equivalent to the product rule in differentiation. It's a formula that allows you to integrate products. Now, you have to be really careful here about who the f and the g is, right? Because it's f times g. And I'm picking this fella as to be f and this one to be the g. Now, normally, don't you just pick the first one as f and the second one as g? Right? First, second, f, g. And it doesn't matter, right? When you do differentiation, for instance, it doesn't matter, right? But normally you pick the first as f and the second as g. But in integration by parts, you pick the first one to be the one that you know how to differentiate, and the second one should be the one that you know how to integrate. I know how to differentiate this guy. I know how to integrate this guy. If I switched places, do we know how to integrate log t? No, we don't. Right? We don't know the integral of log t, right? It's not standard. So what does it look like? It's f of t, capital G of t, take away the integral of f dashed of t, capital G of t, dt. And that's the formula that I would use for integration by parts. Some of you got a different professor and you use the technique called the UDV method. And that's totally okay. It works, you get the exact same answer. But this is the formula that I'm going to use for integration by parts. So let's see what all the pieces look like. F of t is this guy, times capital G of t means the antiderivative of g. Well, if you find the antiderivative of t squared, it's add 1 to the power and divide by the new power. So it's that guy. Take away the integral of the derivative of log, which is 1 over t, times the antiderivative guy, which is 1/3 t cubed dt. Now this guy looks a little bit nicer if you put the powers first and the log second. So that's just cosmetic. And this partially cancels with one of them, and I'm left with 1/3 t squared. And you keep doing this process until there's no more integration left to do. Well, if I want to integrate this guy, it's simply a power rule. Add 1 to the power and divide by the new power, and there we're finished. So all of this is the integral of that guy. Any questions about integration by parts? Okay. Let's find a question to do then. Question 19 from the homework, or at least one that looks like it, is the integral from 0 to 1 of 0, 7 over 1 plus t squared, and 4t cubed over 1 plus t to the 4. So if we want to integrate this, we break it into its individual pieces. And the only reason I'm writing this one down is for completeness sake. Would you agree that the integral is 0 is 0? Right, you're not going to get anything out of that. Now, this fella is the second one. Okay. What is the antiderivative of 1 over 1 plus t squared? I'll give you a clue. It's an inverse trig function. What is the antiderivative of 1 over 1 plus t squared?
Tangent. Yeah, tangent something.
Yeah, inverse tangent. Arctan.
Oh,
Don't
okay.
like arctan, but inverse tan. So this guy is 7 inverse tan of t. And then we're going to evaluate it at t equals 0 to t equals 1. So that's going to be 7 tangent, inverse tangent of 1. Take away 7 times inverse tangent of 0. The inverse tangent basically means what angle has this tangent. So when you're looking for the inverse tangent of 1, you're looking for an angle whose tangent is 1. And the angle whose tangent is 1 is pi upon 4. Right? Tangent to pi upon 4 is 1. Inverse tangent of 1 then is pi upon 4. It's like a two-way street. So this is 7 pi over 4s. What angle has a tangent of 0? Because that's what inverse tan of 0 is. What angle has a tangent that's equal to 0? Any takers? There's an angle out there. If you find its tangent, so it could be 0, it could be pi, it could be pi upon 3. I mean, it's in a unit circle.
I think
Which
it's
one
3
gives you
pi
0?
over 2.
Oh, interesting. That one gets you infinity. But that's the other extreme. Last chance?
Is it just pi?
No. You're bouncing around the right answer, and maybe it's me again. It's 0. What angle has a tangent of 0? The angle's 0, right? Tangent of 0 is 0. So take away 0. Now this fella the last one in the puzzle. That one, I think I'm going to have to do more work. So I'm just going to find what it is and then put the answer down here at the bottom. So I'll just do a dot, 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 dot for now. Okay. So when you see something that's complicated, you probably want to think of what method would I use? What method would we use to integrate this? Choices. Is it a power rule? Is it an integration by parts, or is it a use of? That's the only guys in town. What's that guy?
I think substitution will work.
It does. So who's the use of going to be in this question? Again, it's in, you know, typically use subs are in the question, right? It's not something you can't see. It's one of the things you can see. So who is it?
T to the fourth.
You want to add a little piece to that and it's good.
1 plus.
Well done. So if you differentiate then with respect to t, you get 4t cubed. If you then do the crossover, and you always finish by dividing, in this case by 4t cubed, to isolate the dt. When you do a u sub, your normal goal is to get what is dt equal to. That's what you're after, right? What is dt equal to? So you go over here, and you now have 4t cubed over u. The dt turns into, oh, that's too good to be true, 1 over 4t cubed du. If things work out well, they might not work out quite as nice as this one, but it did. You are now looking at a much simpler integral, right? And that integral is the natural log of u, which then gets turned back into our friend here. So our integral is going to be the integral from 0 to 1 of the natural log of 1 plus t to the 4. So that's going to be from t equals 1 to t equals 0. Right, so plug in 1, you would get the natural log of 1 plus t to the 4. 1 plus 1 to the 4 is 2. Take away, well, you don't want the other answer, do you? 1 plus t4, that's a 1. So you're going to get the natural log of 1. Okay. What number is the natural log of 1? What is the value of the natural log of 1? Come on, guys, I'm dying here. Have a shot. What is it equal to? Or grab a calculator and type it in. You can find out what it's equal to.
0.
It is 0. And this guy here ends up being that. So there is your integral. You see, there's a lot of work in just one question here, because you're going to have to integrate 3 things. Okay, that wasn't a lot of work, but in general, you're going to have a lot of work. You might have a simple, you know, just remember what an integral is. You may have, probably will have, at least one u sub or one integration by parts question to do. Let's see if I can pick another integral. I kind of dotted around the place. Okay, The next one I'm going to do is a version of question 11. And it's going to be the integral of secant squared t, comma, t squared plus 1 to the power of 7, and a t squared natural log of t dt. And this particular one doesn't have limits of integration. So when you don't have a limit of integration, technically you add a plus c, and I'll show you what that looks like in WebAssign. Do you see they already gave you the plus c, right? So it's there. So all you need to do is find out what these guys are. And do you notice they do it in the IJK notation, but I turn them into this because I find it much easier for me. So let's find out who each of these pieces are. I need a secant squared t, the integral of it, dt. I need the integral of t squared plus 1 to the 7 dt. And I need the integral of t squared natural log of t dt. And each one of these guys, right, will integrate on its own. First one is just memory. Do you remember what the integral of secant squared t is? It's a standard integral. It's in the trig family. What's the integral of secant squared?
Just tangent of t.
So it's just tangent. Technically speaking, tangent plus c, but they did the plus c for us, so we don't need to put it in here. So we can just call it tangent t. What method will I use to integrate this guy? It's okay to be wrong. God, the number of times I'm wrong is scary. What would you do to integrate that? What method? It's a power rule, it's a U sub, or it's an integration by parts. That's all you got to pick.
I'd say integration by parts.
Because it looks like two things multiplied?
Yeah.
Yeah. If it wasn't integration by parts, would you agree U sub would be the next candidate?
Yeah.
Right, now, if you try to do that as integration by parts, can you trust me that once you've done about one line, you'll know that it doesn't work? But that's okay, because if you know it's not that one, you know it's the other one, right? So it's not going to like be, 10 hours later, I find out I'm wrong, right? One line of working, you know that this isn't going to cut it.
It
So
does feel like that on the test.
it kind
That
of
was
does
frustrating.
sometimes. Yeah. So are we happy that that would be the use of? The guy inside the brackets is a typical use of, right? This guy here. So, a side issue. If you ever see t e to the 2t, t cubed log t, t squared e to the t, I've done that one. Somebody else. Oh, t squared sine t. If you ever see that kind of shape, it's typically some power of t followed by an e, a log, or a trig function, right? If you ever see that pattern, integration by parts is a good chance of being the method. And it's not foolproof because there are exceptions to every rule, but you see that has a kind of look to it. If it doesn't fit into that very, very rough structure, it's more likely to be a U sub. So do you see that one doesn't look like TE to anybody? It looks like two things, just two things. So in this case, U sub it is. And differentiate. Do the crossover. And then divide by 2t to isolate the dt. And it's standard. You now go the integral of t u to the 7. And dt gets replaced by 1 over 2t du. And then you get some cancelling. And normally, if you've done it correctly, normally, shouldn't you end up with only u's? There shouldn't be any orphan t's floating around. So this integration, which is very difficult to do, has been converted by substitution to this one. This one is a power rule. Add 1 to the power and then divide by the new power. And then turn it back into t's. So here is your guy. 1/16 t squared plus 1 all to the power of 8. Now, the last one in the list. Integration by parts or U sub. Remember what I said earlier about things that work. Remember this, guys? Anything that looks like that is an integration by parts. Would you agree this fits into that category? Right. Now you're doing integration by parts. You need to pick an F, right? And you need to pick a G, right? And whatever the F is, you differentiate it. And whatever the G is, you integrate it. Okay. In this case, pick that guy as F and pick that guy as G. In fact, I don't know if we did this one, but didn't we do one very like it earlier? So you are F and you are G. And the formula is F of t, capital G of t, take away the integral of F dash G, capital G of t, d of t. And F of t happens to be the natural log of t, and so its derivative will be 1 over t. And g happens to be t squared, so its integral is 1/3 t cubed. So we put all the pieces together, I get a t. I get a log t, there we go, times 1/3 t cubed. Take away the integral of 1 over t times 1/3 t cubed. That guy looks nicer if you put the power at the front and the log at the back. This guy, if you cancel, you get 1/3 t squared. Add 1 to the power and divide by the new power. Get that. And there we are. This piece here is 1/3 t cubed, natural log of t, take away 1/9 t cubed, plus a c, but Weber sign gives you the c, so you don't need it. How are we doing, guys?
It's a lot of info.
It's a lot to take in, but it's to do Calc 3, you need to know everything. Well, maybe not everything, but you need to know a large part of differentiation rules and integration rules, right? Now, there are lots of things you don't need to worry so much about, right? For instance, isn't there some special integration rules that you need to be careful about? You know, and things like logarithmic differentiation and implicit differentiation, those kind of things aren't going to crop up here. But the major stuff is, right? All the major techniques are differentiation, product rule, quotient rule, chain rule. And for integration, power rule, U subs, and integration by parts.
For like calcs 3 and for this calc and then calc 4,
Yeah.
does stuff like the fundamental theorem of calculus ever come up again?
The fundamental theorem of calculus is basically telling you how to find the area under a curve, right? So, yeah. There are other things called fundamental theorems of, but they're not that one, right? There's a thing called the fundamental theorem of line integrals, which you do in Calc 4, but that's nothing to do with what you're saying here. Normally when they stick the word fundamental in front of something, it just means it's really important, right? It's really useful. It's fundamental, I guess, as the name kind of implies it. Right, I've been jumping around here, looking at various things to differentiate, looking at other things to integrate. I'm trying to find one more integration if you hadn't already been overwhelmed by enough integrations. I'm picking this as the last integration question unless you tell me otherwise. And because it's going to be the last one, I'm going to pick a trig one, which we haven't really dealt with. I'm going to pick a really ugly one, working on the principle, if you can do the ugly ones, aren't the easier ones going to be okay? So this is the final question, or at least a version of it. Question 20 is the last homework question. And we are being asked to find the integral from 0 to pi upon 2. And the function is 6 sine 5t cosine t, comma, 3 sine t cosine squared t, and lastly 8 sine t cosine t. Start with the first one. First one is 6, that guy, cosine t dt, right? It's still integration by parts or u sub. It does not look like an integration by parts. Wouldn't it have to be t squared sine t, t cubed cosine t, right? Since it's not an integration by parts, by a process of elimination, this guy and actually all of them are going to be u subs. When you do a u sub and the combination are sines and cosines, your u sub will always be one of two things. It's sine t, that's all, or cosine t. Pardon me. Sine t on its own or cosine t on its own. One of them works typically and the other one doesn't. That's as simple as that. So when you were doing Calc 2 and you were integrating trig functions like this, which one would you use as your u sub, sine or cosine? And there is a kind of rule, which I'll tell you in a second. Sine or cosine? If you're a good gambler, you're going to guess right.
Probably cosine.
Okay? Don't go to Vegas, Calvin. So here's the rule. When you've got a power of sine and a power of cosine, as we have here, right? 5 of them and 1 of them. Always pick the bigger one as your u sub. Okay? Always choose the larger of the two as your u sub. Okay? Now, if you differentiate with respect to t, why did you think it was the cosine? Is because it was on its own?
Kind of it was on its own, and also because it turned. Oh, yeah.
Oh, yeah.
Where I got confused.
Uh-huh.
For some reason, I thought we were taking the derivative.
Ah, okay. Right. But I got an aha moment. Aha moments are good, right? Because you kind of see where this is leading to, I hope. Now, if you do the crossover, if you then divide by cosine t, you now have isolated the dt. So let's see what we got. We got a 6. That piece there is sine t to the power of 5. So that guy becomes a u to the 5. And the cosine t, and then you replace the dt by 1 over cosine t du. Just like magic, that happens. And we are now looking at this integral, which is clearly a lot simpler, and it's a power rule. So I'll add 1 to the power and divide by the new power, which gives me that. I'll then turn the u back into a sine, and there we go. The first piece, like this guy here, is going to be sine that fella, evaluated at t equals 0 and t equals pi upon 2. Come on. Right. Middle one. The integral of 3 sine t cosine squared t. Right, now, bear in mind what I just said up here. Remember, the rule is if you have a sine and a t, a cosine combination, isn't your u sub the bigger power? So in this case, cosine t, right? Cosine t, because there's a square. And if you go through the generic process, remember the derivative of a cosine is negative sine. If you do the crossover, and then you divide everybody you have now isolated the dt. So it's going to be the integral of 3 sine t u squared 1 over the negative of sine t du. Those guys cancel. And you now are looking at the integral. Oh, it's negative, so negative 3 u squared. Power rule. And then turn it back into cosines. So this integral is equal to negative cosine cubed t. So it's going to be negative cosine cubed t, evaluated at t equals 0 and t equals pi upon 2. And the last one is 8 sine t cosine t dt. Now my rule was, if you've got combinations of sines and cosines, pick the larger power as your u sub. Do you see in this question, it's a draw, aren't both of them 1? Right? Sine t, is there only 1 power of it? Cosine t, there is only 1 power of it. So the u sub here can be either 1, both work. So that's kind of exception to the rule where one works and the other doesn't really work. This works, no matter which one you pick. So if you differentiate this guy, you'll get negative sine t and there's the isolated dt. So we now have 8 sine t cosine, which is u, dt, which is this guy, du. Cancel, cancel, and you're now looking at negative 8u. If you do the power rule, add 1 to the power, divide by the new power, you get that. And then you turn it back into cosines. So the last one is negative 4 cosine squared t and then you evaluate it at t equals 0 to t equals pi upon 2. Now, to save time, I'm just going to pick one of them and say, look, do the same thing for each of them. If you took this one, right, and you evaluated it at pi upon 2 and that's 0, you're going to get that guy take away that guy. Sine of 0 is 0, 0 to the power of 6 gets you big 0. The sine of pi upon 2 is 1, 1 to the power of 6 gets you 1. So the answer would be, for that guy, would be 1. And you do it for this guy, do it for this guy, and so on. Any questions? Or maybe there's a lot to think and absorb, which is fine.
Just trying to write everything down quick enough.
Well, you know, if you watch the video, you can always pause it and catch up. So it might be easier sometimes just to listen and then, you know, because there's a lot being written here and you might miss a line. So where are we off to next? Well, there are some things that we haven't done. In particular, we're going to find a thing called that guy. It's called the unit tangent vector. Another thing we're going to do is we're going to find the equation of a tangent line. In 3D. And the last thing, although I might do them in a different order, is we are going to find these guys. The cross product of a first and second derivative. And the dot product of a first and second derivative. Okay, so I think what I'm going to do is I'm going to do that one first. So there are a couple of questions. I'll see if I can find their numbers. Where you do what I just said. Question 4 is asking us to get that guy, amongst other things. Question 5 is asking us to find that guy. Basically, that's the cross product of a first and second derivative, and this is a dot product of the first and second derivative. Just checking. Okay. So you get one example of this, one example of that. I'll have to pick my own. So, well, maybe not. The questions are varied enough that it won't matter. Right. So in question 4, or at least a version of it, you're given a space curve, and it's, at least in my example, it's going to be 2t, 3t squared, 3t cubed, right? And we are going to be asked to find the cross product one. So first thing you do is you find the first derivative, which is 2, 6t, and 9t squared. Compared to what we've done, would you agree that's not a hard derivative to find? And then you find the second derivative. Well, differentiate 2, you get 0. Differentiate this guy, you get 6. And differentiate this guy, you get 18t. Are you comfortable with those two guys? Now, In question 4, they ask you to find this cross product. So if you take the first derivative and you do a cross product with the second derivative, we're going to set it up the exact same way we do all cross products. It's going to have an I, it's going to have a J, and it's going to have a K. The main difference is that these won't necessarily all be numbers, right? Some of these are going to definitely contain T's. So for instance, this row goes here, 2, 6T, 9T squared. This guy, right, goes below it, 0, 6, 18T. Are we good? Setting up a cross product the same way you would have done if these two vectors were nothing but numbers. And then our answer is going to be so many i's, take away so many j's, plus so many k's. Right, you want the first one. Right. Cover up column I. Let's see what the difference is, if there is any. Don't you do major diagonal, take away minor diagonal, right? Right, major diagonal, and I don't have a calculator, darn it in space, I always leave it in my office. It's 60 plus 48, 180 squared. Major diagonal. Take away minor, which is take away 54 T squared. Now you want the middle guy? Major diagonal, 36T, take away nothing. You want the guy at the end? 12, major diagonal, take away nothing. And so your answer will be, well, they actually combine to give you 54 T squareds. That guy is take away 36T, and that guy is 12. Not too bad once you kind of follow the process. Find the first derivative, find the second derivative, set up your usual matrix, I, J, K. All the I's, take away the J's, add the K's, tidy it up, you're done. We good? Let's do a dot product, which is a version of question 5 then. In question 5, it's my version of the space curve, is 4e to the 3t, 2e to the negative 3t, and finally 4t e to the 3t. Find the first derivative. This is a chain rule. You'll end up with 12 of these guys. This is a chain rule. You'll end up with negative 6 of these guys. This is a product rule. You will end up with 4 of these plus 12t e to the 3t. And you're going to have to check that yourself, but that's what you get. Now you get the second derivative. You just differentiate these again. This guy, chain rule, you get 36 of them. This guy is a chain rule, you get 18 of them. This guy gets you 12e to the 3t. And this guy, if you use the product rule on it, you're going to get 12e to the 3t plus 36t e to the 3t. And then just tidy it up a little bit. Get 36 of this guy. You get 18 of this guy. And those come together to give you 24 plus 36. Much uglier, I think, than the first one. So you've got a first derivative, a whole load of stuff. You have a second derivative, a whole load of stuff. You are now going to be asked to find dot product of the first and second derivative, which means this guy here times this guy here. 36 squared is 12 squared, so it's 144 times 9, so it's 900, can't do it. It's whatever 36 squared is. And you multiply these together, you just combine the powers, so that's the first one. And if you do the second one, it's this guy times this guy, and that ends up being whatever 18 squared is, and when you multiply these together, you just add their powers, and you get that again. And then last, you got this guy here, and nobody's told me, I've just done it. There's my r dashed of t, not this one. There's my second. Yep, let's start again. This guy times this guy is going to be whatever 12 times 36 is, e to the 6t. Now that's better. Plus, so it's not a vector. The middle term, which is this guy, times this guy. So that's going to be take away 6 times 18, e to the negative 6t. And the last one is going to be this guy times that guy. So you will find this fella times this fella. And that horrible mess is your third answer. And it's just got too many numbers for me to do in my head. It's just a mechanical foil, but really ugly. So you're asked to find the cross product of two, which wasn't too bad, and the dot product, which was ridiculously ugly. And we are done. Any questions about that guy? Apart from the fact it's ugly. Okay. Let's do the equation of a tangent line. Okay. The equation of a tangent line, let's find an example of that. So a version of that would be question 7. That's it. So there's two examples of this. Here is a space curve. It's the square root of t squared plus 3. It's the natural log of t squared plus 3. And it's a t. And we're being asked to find the equation of the tangent line at the point 2, natural log of 4, comma 1. So can you imagine what you have here is a space curve, r of t, that this point here, let's say it's there, that guy there. Then there is a tangent line that goes like that red line. And we're going to find the equation on the line. It could be sticking out, right? It's going to be a vector equation. To find the equation of any line, including this one, you need two things. You need to have a point on the line, which is pretty much that guy. So I don't need to go looking for it. And you need to have what's called the direction vector. Now, the direction vector is essentially the derivative. And I am going to differentiate this guy, and I'm going to have to plug in a value of t that corresponds to this point. Have you noticed that they haven't told us what t value generates this point? So if you look really carefully, this guy says t and this guy says 1. Won't you only get this when t is 1? So what they've done there is they've hidden a little piece of information I need. I need to know what the value of t is. Because when I find this derivative, don't I have to plug in a t to get what the numbers are, right? I need a direction vector that's going to be numbers. So let's see what we get. This guy is going to be rewritten as t squared plus 3 to the half. This guy is going to be left alone, and so is the other one. And now I'm going to differentiate it. And then after that, I'm going to plug t equals 1 to get our direction vector v. This fella is a chain rule. So you multiply by the power, reduce the power by 1, and then you finish with the derivative of the inside function, which is 2t. So if you tidy this up, they 2's cancel, you've got a t. This guy goes downstairs, and there's a t squared plus 3. Right, half powers downstairs, square root. This second one is a chain rule as well. If you differentiate a log, you get 1 over the thing, times the derivative of the inside function is 2t. So this guy becomes 2t over t squared plus 3. That guy just gets you 1. So there is our derivative. How are we doing with that one? You okay with where each of the pieces came from? Kind of skipped one line to get from here to here. Now, you want to find what the derivative is when t is 1 because of this. So it's going to be 1 on the top. 1 squared plus 3 is 4. Square root of 4 gets you 2, so that's a half. T equals 1 gets you 2 on the top, 4 on the bottom, which I guess now that I know it, it's a half, and that's a 1. So it looks like the derivative at 1 is the vector 1 half, 1 half, 1. And that is our direction vector that we're looking for. So I want to find the equation of a line that passes through the point 2, log 4, 1, and has a direction vector of 1 half, 1 half, 1. But you put this information together then, what do you get? You get 2 plus a half t. You get log 4 plus a half t. And you get 1 plus 1t. And that is the equation of the line written down in parametric form, which is what they wanted.
Where did the 1 come from? In
This
the
one here or this one?
our for the derivative of RT, how did you get the derivative R parentheses 1?
This is am I pointing at the one you're thinking about?
No, on your lower left. Like that,
Oh,
you know,
that one
that
there?
arrow R parentheses 1, that one, yeah.
It came by evaluating the derivative at t equals 1. So, where did the 1 come from? Here is the space curve. What value of t would generate this point, right? Well, I just matched up the z's. T has to be 1. T equals 1. if I matched up the middle one, wouldn't the log of t squared have to be the log of 4? And wouldn't that 1 plus 3 gets me 4? And if I did this one, wouldn't t be 1 and 1 plus square 3 gets me 2? So 1 works. You see that t equals 1 generates it. And I just looked for the easiest one to solve. I don't need to solve all 3. I just need to figure out one that works.
Okay, gotcha.
Okay.
Thank you.
Gotcha. How we doing? Any questions about how to find the equation of a line? Right? Tangent equation of a line, I should say, that passes through a point. So the last guy in town. Wait a minute. Do you want me to do a second example of the equation of a tangent line in 3D? Was that one I gave enough? Or do you want to see a second?
I think one more. Yeah.
One more. Okay. So let's pick this space curve. Just put lots of little pieces in. And we want to find the equation of the tangent line at the point P, and let me make something happen. 1, can I put a 2 there? Yeah, that's better. At 1, 2, 1. So the question is, find the equation of the tangent line to this curve at the point 1, 2, 1. So before we start finding derivatives and all sorts of other stuff, don't I need to know what t value would generate that point? Because I need to know it when we get to the derivative bit, right? And I plug in a number. What value of t would generate the point 1, 2, 1? Well, pick anything. Pick the x's.
0.
Yeah, that's all you do. Would you agree 0? Let's suppose you decided to pick the y's. 0. Let's suppose you decided to use the z's. Oops, forget that. Here we go. The only way cosine t would equal 1 would be, right, if t was 0. Now, I know there's other answers, right? Pi and 2 pi and whatever else, right? But none of those other answers work with these two. Would you agree 0 works with all 3? That's why I know. In this case, we're going to be doing it at 0. So now I find the derivative. This one is a power rule. This one is a chain rule. So it's not just 2e to the 2t, it's 2 times e to the 2t times the derivative of that, which gets me another 2. So that's where this guy comes from. And if you differentiate a cosine, you get a negative sine t. Are you comfortable about the derivative? Right. Now you evaluate the derivative at 0, because that's what generated this point. And you get 2 lots of 0 is 0. 4e to the 0 is 4. And this guy gets you negative 0, which is 0. Same worse. This guy is our direction vector. So we're going to have the point 1, 2, 1. And the direction vector is going to be 0, 4, 0. And if you want to get the equation, it's 1 plus 0t, 2 plus 4t, and 1 plus 0t. So there is the answer in parametric form. The equation of the tangent line. Are we good? About to move on.
Yeah.
Our last thing. Well, that I've said that, I realise there's one more after this, but that's fine. Always do that. Always forget one little guy. We are going to find what is called the unit tangent vector. He is typically called capital T of t, but most of the questions we're going to be finding the unit tangent vector at a point, like the unit tangent vector at 0, or maybe the unit tangent vector at 1, or maybe the unit tangent vector at pi over 2. Right? So you tend to evaluate it at a specific point, mostly because it's really ugly if you try and do it in terms of t. It's possible, but it's typically really ugly if you want to do that. So the kinds of questions that use or ask you to do a unit tangent are questions 2, 3, 4. So it's happening a lot. 5. There might be one more, just let me see if there is. Yep. 17. That's it. So there's what, 5 different situations, 5 different questions. And a lot of these questions don't just ask for one thing. So this question might find r of t, r dashed of t, the unit tangent vector at t, and r1, r dashed cross r double dash, right? They'll ask you A, B, C, Ds. But one of the things they'll ask you for is the unit tangent vector. So before we calculate it, let's kind of show you what it is. There's my classic space curve, right? My r of t. Now, if I find the derivative at some point, right, let's say at t equals 1, then you're going to get that guy there, right? Going to be a vector. The unit tangent vector is just that vector, but it's a unit long. So it's just basically the first derivative, but 1 unit long. So imagine I give you a space curve, and it's t cubed, 2t plus 1, t squared, and you're being asked to find the unit tangent vector at 1. Step 1, find the derivative. So 3t squared, 2t. Just find the derivative. Step 2, find the derivative at 1 in this case. So that's going to be 3, 2, 2. Step 3, find this guy's unit vector. So how do you find a unit vector? Well, don't you find the length of this and then divide everybody by its length? So essentially, the formula for a unit tangent vector at 1 is 1 over the magnitude of the derivative vector at 1 times the derivative vector at 1. So the magnitude of this vector is the square root of 3 squared plus 2 squared plus 2 more squared. That's 9, 9 and 4, 13, and 4 more is 17, so it's square root of 17. And so the unit tangent vector at 1 is going to be 3 over root 17, 2 over root 17, and 2 again over root 17. So you take your function, you differentiate it, you plug in whatever value of t you're being asked to find a unit vector at, in this case 1, get an answer involving numbers. This vector, basically this guy here, you're going to now find its unit vector. So that means find its magnitude So you really don't need this formula. Find its magnitude and then divide this vector, the original derivative, by that magnitude. And this guy is called the unit tangent vector. How's that going? Okay, see if I can find an example. Let's pick 3. In question 3, you're being asked to find the unit tangent vector at 0. And your space curve is cosine 8t and 2 sine 3t. Oh, and we're being asked to find the unit tangent vector at 0. So, differentiate. Okay, what's the derivative of cosine? Just derivative of cosine.
Negative sine.
That guy is 8, and this guy is a chain rule. So you eventually are going to get 6 cosines of 3t. You all happy about how come the 2 turned into 6? Because the derivative of 3t generates another 3. Right? You then find your derivative at whatever that number is, 0. Negative sine of 0 gets you 0. 8 just gets you 8. And 6 cosine of 0s get you 6. We're going to find the magnitude of that guy, divide this vector by the magnitude, and that's the unit tangent. So the magnitude of this vector is 0 squared, 8 squared, and 6 squared. Square root of 100, I believe, and it's 10. So the unit tangent vector is this unit vector here, right? So this guy divided by 10s. So 0 divided by 10, 8 divided by 10, 6 divided by 10, and I simplified it as I was doing it. That is your unit tangent vector. How are we doing? Are they a little bit easier than some other things? Find the derivative, evaluate it at this number. This vector is then converted into a unit vector, and that's your unit tangent. That's the answer. Do you want to see one more? Or are we good with those? Any preference? Okay then, let's show you the definite. Oh, I get something in chat. Right. Let's show you the last piece of the puzzle. Here are 2 questions in your homework. This is question 8. Shrink that little bit so you can see the whole thing. Here is question 8, and if you look, you can see question 9. And you have a curve called R1, and you have a second curve called R2, and they intersect at the origin. And you're being asked to find out the angle of intersection. So can you imagine that you might have a situation looking something like this? You have at the origin 2 curves coming together. So first curve might look like that, and the second curve looks like that. And if you zoomed in right at the origin, the 2 would intersect. So if I did a kind of close-up version of it, one of them might look like this, and the other one might look like that, and there's the origin. the angle at which they intersect is theta, and we're trying to find that angle. Now, I know these are curves, but if you zoom in and zoom in and zoom in, don't they eventually become quite straight looking? And if you could zoom in infinitely, they would be essentially straight. So we have our first curve, which is 2t, t squared, t cubed. And we have our second curve, and it is the sine of t, the sine of 5t, and then 4t. To find the angle at which two curves intersect, and in this particular case, they intersect at the origin. Now, if you're going to be the origin, t is going to be 0. If you're going to be the origin, t is going to be 0. That's going to be important later, right? The value of t that makes the origin happen is 0. So if you want to find the angle, what you do is you find the derivative. So the derivative of this one is 2t, 3t squared. And you find what it would be at 0. And that ends up being 2, nothing, nothing. Okay. You then take your second function, which is this one, and you find its derivative. And if you differentiate a sine, you get a cosine. If you differentiate this guy, you get 5 times cosine of 5t because it's a general. And if you differentiate this guy, you get 4. And you also find out what does the derivative look like at 0. So you're basically finding what the direction vector for each was. So the first one is 2, 0, 0. This one here is going to be 1, 5, 4. So if you imagine you've got two vectors and you try to find the angle between them. This is like R1. And this is like R dashed 2. And we have a vector for each. So if I ask you what angle the two vectors cross at, then we would use our dot product formula. So I might as well just call this guy U and V. So the cosine of the angle theta is the dot product of the two divided by the magnitude of the first one times the magnitude of the second one. So if I do the dot product, it's 2 times 1, which is 2, plus a lot of nothings. If I do the magnitude of that, it's going to be 2. If I do the magnitude of that one, it's going to be 25, 26, 36, 42, I believe. And theta is going to be the inverse cosine of this guy over that guy, which I'm not even going to bother to tidy it up. It's that guy, right? And then you would just get the angle. Since I have no calculator with me, I'll pretend it's 53 degrees. And that would be the angle between the two. So let's show you that one more time. Here is your first curve. Here is your second curve. Since they intersect at the origin, we know that t is 0. We differentiated this guy and plugged in 0 and got its direction vector. We plugged this guy, we differentiated this guy, plugged in 0, got its direction vector. We then just found the angle between them using the dot product. Now, if you did this question here, your first job is to find out where they intersect. and whatever that point is. And then once you know that, you do this. So let's put that down, I guess. It's the last thing. So I have a curve that is equal to, oops. It's a lot to take in. I understand that. There's an awful lot going on. I hope what you might be able to do is go back to this video and just go to the bit and then just, watch it and then do some examples and then, get them comfortable in your brain and then watch another bit and then do the examples and kind of break it into manageable chunks and then go and have a coffee and come back the next day. So here's the first guy. And the second function is using s, interesting, different variable name. And it's this fella. And essentially we have two curves, right? That's maybe R1 and this could be R2. And we know that they intersect, the question wouldn't make sense. What we don't know yet is where they intersect. So if you have two curves and you want to know where they intersect, if you match the x's, you get that, agreed? This x equals that guy. If you then match the y coordinates, this guy equals that guy. Okay. If I tried to solve these two, can you trust me, it doesn't work. So I'm going to match. Well, by saying it doesn't work, all the variables disappear and I don't know what the answer is. So I'll take the first one and I'm going to match now the third one, which is this guy, equals, is that s squared? Yes, s squared. So I'm going to call that equation 1. I'm going to call this equation 2. If I plug t for that in here, I get 48 take away this guy squared equals s squared. If you FOIL this out, you'll get 64 take away 16s plus an s squared equals an s squared. They cancel out. This guy and this guy gets you 112. Take away 16s equals 0. If you don't like these cancelling out, how about subtract s squared from both sides? It has the same effect. Here, I get that. And so s is going to be 112 divided by 16. What on earth is that? Is that going to be 4, 5, 6? That looks like it probably won't simplify much, but I'll try. 2 gets me 56. 2 gets me 56 over 8. Oh, would you believe it? 7. That actually comes out nice. So I know that s is 7. And I know that t is 8 take away s. So that makes t1. So these points, these guys intersect at a point when s is 7 and t is 1. So I'm going to find who the coordinates are. If I plug in 1 here, it's 1, 2, 49. And if I plug in 7 here, it's 1, 2, 49, right? Matches. So that all that hard work was only to find the point where they intersect. And as part of that, we now know that we have to use t equals 1. And when you're using this guy, we're going to use s equals 7. So you take this fella, the one with the t's, and you differentiate them. You're going to get 1, -1, 48 plus 2t. You plug t equals 1, and you'll get the direction vector at that point. It's this guy. You find the derivative of the second function with respect to s, and you get -1, 1, 2s. You plug in 7, and that'll tell you what the direction of this guy is at 7, and it's going to be -1, 1, 14. Running short of time here. U is that guy. Call this guy V. Can't we find the angle between two vectors using the cosine of theta is u dot v divided by the magnitude of u times the magnitude of v, and according to what I have in front of me here, tell you what the answer to that one will be, or not. Cengage has decided to close up. So it's 57 degrees because I decided it's 57, but you'll get the real value when you do it. Well, I'm glad you hung in to the end. A lot to take in. Hopefully you'll be, over the next few days, you'll have a chance to catch up on your integration and your differentiation that you might be a bit rusty, and maybe get some time to watch the video a second time, or even a third time if it takes that, to do each of the different kinds of questions. I suggest, like I said earlier, I'll just repeat myself, just read or watch the bit that does one job, like the bit that just finds the first derivative and then get comfortable with that. The bit that just finds the integral, get comfortable with that. Then do the bit where you do R1 cross R2 and R1 dot R2, get comfortable with that. So take each of the major types of questions, look them over, see what they're like, then do the homework that corresponds to that. And hopefully you won't have as much problems. Any questions before we call it quits for today? Right, I'm going to hang about for homework questions or maybe other questions to do with this. Otherwise, have a nice weekend. Although I suspect it might be a bit tough, but do your best to enjoy it. Then I will see you on Monday.
All right, thanks, Professor.
Right.
Thanks, Professor.
You're
Don't
welcome.
we not
Bye-bye,
have class
guys.
Monday?
Say again?
Don't we not have class on Monday?
Yes, we have. Why
The
did I
10th?
say again?
The 10th, I thought we didn't have class on Monday. It's Indigenous Peoples Day.
Goodness gracious me. Is it? I don't know.
Yeah.
Is Monday a holiday?
Monday the
Something
10th.
back-
It's also in the syllabus that we don't have class that day.
I'm not saying no to that because I don't keep track of holidays. Let me check it. There. Oh. Do you like my little portable keyboard?
I like it. It's
Yeah.
nice.
Yeah. Now back to what I was using. Take me just a few minutes to get into the syllabus and to check it. Because I only see you twice a week, even if it is a holiday, I will make a video on my own some and just put it online and you can watch it whenever, right? Maybe on
Okay.
Tuesday or something, right?
Okay,
But
sounds
let's
good.
just see, if it isn't a holiday, I will be here, and I think it's helpful if you're here as well, because at least you get a chance to say, I need another example of that question. Anyway, I'm almost there. Let's put it on the screen. Is this 163? Make sure I'm in the right place. I am. Okay, let's kick over. And you nailed it. It is a holiday. So there won't be any you turning up. I have no, I don't need, that's a bad phrase. What am I thinking? I don't expect you to turn up. It's your holiday. You should enjoy it, right? What I will do is I'll put a video online that you can hopefully watch some other time, and it will contain that unit of work. And unfortunately, because we only see you twice a week, if we take a day off, isn't that essentially half a week?
Yeah, that's what I was thinking. I just
Yeah.
wanted to make sure.
But you don't need to, and I don't expect you to turn up, right? So enjoy your Monday. I'm
Okay.
not
So
going
the
to say, oh, I expect you to turn up. I don't expect you to turn up.
already. So the video will be up just like Tuesday sometime.
I'll probably put it up on Monday because